Okay. Okay, you guys can see my screen, right? All right, well, thanks. Thanks a lot for the invitation. I'm actually very excited and a bit flattered that you invited me to give this talk. And I hope that you can interrupt me a lot, and let's do our best to replicate the sort of fun of meeting in person. I made the mistake, I think, while I was preparing this talk, of looking up the previous talk that you had posted on YouTube by Ard Louis. And let me just say, that's a tough act to follow. That's hard to live up to. So I feel like the best course of action is for me to just disappoint you up front and tell you that I'm not that interesting, not as interesting as he was. Nonetheless, my understanding, oops, what happened here? Oh, sorry, I started from the wrong slide. Nonetheless, my understanding is that this talk is supposed to be, have some biographical element to it, where I sort of tell you a little bit about, what my path was to getting into physics, to becoming a physicist, or what I'm interested in, that sort of thing. So, okay, I might as well start at the beginning. Here's me. I'm the fat little kid here. These are my parents. My mom was a stay-at-home mom. She was from some little town in the north of Ontario, some iron mining town. My dad grew up largely in the American West. He was actually a fighter pilot. So here's my dad. He flew an F-16 for about 20 years. And because of that, actually, we moved around a lot as a kid when I was growing up. So, the way the military works, at least when you're an Air Force officer, is you get reassigned every year or two. And generally you move somewhere knowing that you're going to leave again in 10 months or whatever. So we moved a lot of times. Again, that's me sitting in the back of the moving truck. And I think that by the time I went to high school, I had counted that I had lived 14 different places. So that's sort of what my upbringing was like. And I mention it actually because as I was watching your previous talk by Ard Louis, he made this remark that I thought was quite insightful, that in science, you see people from all over the place, but you see, to a large degree, people who have experience being outsiders, feeling like they're outside of some community. And that struck me as an insightful comment and has really rung true in my experience, that, among scientists, you find people from any walk of life you can think of, but it is true that we, by and large, tend to have a lot of qualifications in the field of being foreign, of being someplace that you're not from. And, that's certainly true in my case. I always felt like I was just passing through and was in some place that I wasn't, native to. And if I were to speculate as, why that's the case, I might say that when you're trying to become a scientist, like when you make up your mind that this is it, I'm going to try to be a physicist or whatever, there's going to come a point shortly thereafter where you're in a room full of people and you feel like you're absolutely the stupidest person in that room. Like everyone around you is talking about physics and it all makes sense to them, but you don't even understand the words that are being said. And it's just really disconcerting. And you feel like, what have I gotten myself into? I'm never going to be able to do this. And when that moment comes, you have to not panic. You have to be able to draw on some reservoir of experience that tells you, I've been in a situation like this where I felt like I was completely out of place and I kept going and it was okay. And so I think a lot of us who ended up going into academic science have some personal experience like that we can draw from. And well, this was mine. Okay, so I did pretty well in school growing up in the various different school systems. But I don't think I ever gravitated especially strongly toward math or physics or anything like that, math or science, until 8th grade, and when I first encountered algebra. And actually, the story is that I wasn't in algebra in 8th grade. I was in pre-algebra. I was in some class where they were doing some Mickey Mouse things with fractions and teaching us how percents work and that sort of thing. And actually, as was mentioned to you in that introduction, I did not complete 7th grade, and that's why I was behind. And the story was that at the time, our family was living in Venezuela. My dad had been stationed in Venezuela, and I was just entering my teenage angsty years. I was 13, and I just had a really hard time adjusting to the school and the new culture. And finally, I got to a point where I just felt like this whole country sucks and everyone in it sucks. And I told my mom that I was not going to attend school anymore, just put my foot down. So she pulled me out and I stayed home for 6 months. And when the next school year came around, she by some amazing act of diplomacy, got me accepted to a different school into 8th grade. So I never completed 7th grade. And consequently, I'm behind. I'm way behind in math by 8th grade, and I'm doing fractions and such. But I had a friend who was doing algebra, and I remember just looking at it and thinking it looked really cool. Like it looked like some cool little logic puzzle where letters stand for numbers and you have to figure out what they stand for. And I just remember thinking it was cool and trying to get him to tell me what he was doing. And when he would explain to me a little bit, I finally just went up to the algebra teacher and sort of begged my way into the class. I'd be like, let me just try it out. And if I do badly, you can demote me again. So I got into algebra in 8th grade and just really loved it. It was like the first time where school felt just really natural and engaging to me. So then, I mean, the story of the rest of my education is really me one time after another begging my way into a class that I wasn't prepared for. So getting into algebra 2 and then begging my way directly into calculus because I thought it was cool. And calculus was the most amazing thing I had ever seen. I just thought it was like the most beautiful, most all-encompassing thing that you could learn, and just was really excited by that. Anyway, okay, so eventually I got to the end of high school. And I ended up going to college at Virginia Tech, which is a school in Southwest Virginia. And I picked Virginia Tech kind of at random, not really random, I guess. Well, the truth is that I had friends who were going there. And so that's why I went there. At some point during high school, I had lived in Virginia and I had some friends and they were going, and it seemed as good as anything else. I had taken one physics class at this point that I thought was pretty fun. But otherwise was not, hadn't been that serious about physics in general. And it never occurred to me to major in something like math, which I had loved, because I felt like, when I had this vague feeling that when you go to college, you're supposed to learn how to make something or build something, do something. And math just, I don't know, like that's something that some different kind of, like the Eulers and the Lagranges of the world learned. And so I majored in mechanical engineering, think that, maybe this way I'll learn how to make cars or something. I picked up a physics major pretty quickly because I was going through the catalog and seeing these courses about quantum mechanics. And I thought, okay, this looks cool and I got to know what this is about. And really the story of my undergraduate education is a story of me, one after another, just trying different things, just being really excited by the whole universe of possible things that one could learn and specialize in. And so I just tried like all the things in this list. And by tried, I mean, I either worked in a research lab, or I got a summer job, or I got some kind of internship, or I took a summer off and worked for a company, or I took a semester off and worked for a company. So I just tried lots and lots of different things. And one by one, ruled out things that I didn't like or that didn't like me. So for me, I guess undergrad was a time where I explored lots of fields and figured out what I liked and didn't like, what I was suited for and what I wasn't suited for. And so by the time I went to grad school in physics, I could confidently say, okay, I don't want to do mechanical engineering. And there are many types of physics that I also don't want to do. I guess I should explain this picture. So this picture is me in the SPS around the year 2005. And at Virginia Tech, the SPS had this tradition where once a year they would host like a special dinner. And the point of the dinner was, it was like a fundraiser for the SPS. The faculty would come and they would pay an entrance fee and we would serve them dinner. And then we would make them sit through like a large set of skits making fun of them. So we would have like 6 different pre-prepared sketches, or like Saturday Night Live style, that just made fun of the faculty in different ways. And that was always one of the greatest things we did. So I made some kind of Weird Al style parody song about our E&M teacher. And that's what this picture is. Okay, so undergrad, I basically just ruled out lots of things that I either was too bad at or that I didn't like. But the one thing that I really liked that just really occurred to me as an exciting thing that happens in the universe was, I guess what I'll vaguely call emergence, was when you're looking at some kind of problem that looks like a complicated soup of a million things interacting with each other. And from that soup, there emerges something simple, some collective excitation, some effective particle, some oscillation mode, something that arose in a simple way out of a complicated miasma. And that's what I really loved. And I eventually realized that, well, if you want to study that sort of thing, you've got to go into condensed matter. And so having ruled myself out as an experimentalist by, breaking many things in various labs along the way, I said, okay, I guess I have to do theory. So I went into condensed matter theory. I ended up going to the University of Minnesota for my PhD. And I was very fortunate there to end up as the student of this guy, Boris Glovsky. So Boris was is a Soviet-trained physicist. So he was trained in the Soviet Union, spent most of his career there, and moved over shortly before the Berlin Wall fell. And he was just in many ways an exceptional and a remarkable scientist, not just in terms of what he was able to accomplish in his career, but also in his style of thinking, and his style of doing physics was very unique. And along that came with a very unique style of training graduate students. So as I'm guessing a lot of you will find out fairly soon, PhD advisors have a whole range of different styles, different ways of approaching mentoring PhD students. And one of the hardest things about graduate school is finding someone whose style is compatible with your own talents and abilities. And I was very lucky to sort of luck into that by accident. But some PhD advisors like to give the student a problem and then just let them hit their head against it for a long time, and occasionally drop by to offer words of wisdom, but otherwise to sort of let the student be independent. Boris was more or less on the exact opposite end of the spectrum. He liked to talk to me every day for multiple hours every day. And generally the way my PhD training would work is that at 9 o'clock in the morning, he would walk into my office and say, Brian, let's talk. And so, okay, I'd go into his office and he would start talking about whatever problem we were thinking about. And he would just start sketching out in conceptual terms the way that he thought the phenomenology of this problem would play out. Just like, oh, I bet this effect is going to happen, and then this other one is going to happen. And then it was almost like a narrative he was painting, like a Russian novel every morning, of all these different effects and what would happen and what the result would be. And maybe there was some math, but it was always extremely simple, algebraic things. And maybe there was an integral on rare occasion, but it was mostly him just like sketching all these concepts for me. And then he would turn to me and say, do you agree? And I would be like, okay, look, I'm the grad student and you're the famous physicist, so I'm sure you're right. And he'd say, okay, well, go think about it. Go think about it and let's talk again after lunch. And then he would always seem kind of vaguely disappointed in me as I walked out of his office. And I'm like, okay, I'm supposed to think about this whole landscape that he just painted for me. And I would go and read something or try to do some little calculation and hit my head against something. Then he would call me back again in the afternoon and then again at the end of the day. So I probably spent 2 to 3 hours talking to him one-on-one every day. And in all of those conversations, at least for the first year, it was him saying, this is my vision, do you agree? And me going like, I don't know, I guess so. And then one day, maybe near the end of the first year, I must have been in a cantankerous mood or something. I said, you know what, I don't agree. Actually, I think it should be, and I pushed back and painted some counter scenario for what he had proposed, that it won't be this thing you said, some other thing will happen. And I remember he got really excited and he's like, aha, now we have a debate. And he started, point by point laying out the case for why I was wrong. And it's not going to be this, it's going to be this instead. But something kind of interesting came out of that rebuttal. And at the end of it, he was very excited. He's like, good, we made some progress. Well done. And that's when I realized that what he wanted from me was to argue with him. Like, my role in this enterprise was to argue against whatever he says, as long as I feel like I can make a reasonable argument against it. And through the course of our arguments, we will arrive at the correct answer. And so I said, okay, I guess that's my lot. And I became the guy who argued with him for 2 to 3 hours every day. And I still have a clear memory of the first time I won one of those arguments where he had said, this is happening and I bet this is why. And I had said, no, I bet it's this other thing instead. And we had argued it out and he had realized that I was correct. And I remember walking out of his office after losing 99 consecutive and winning the 100th, just feeling like I was champion of the world and was so excited. But anyway, that was my PhD. And in retrospect, that was just an enormous gift to have been given, that I learned to think about physics and I learned an enormous set of different, physical phenomena. And I learned his particular style, which was very unique to him. It's a style of thinking about problems and approaching them. that's really sort of launched the rest of my career is what I was given as part of my PhD training. Again, not every advisor will give you this sort of thing, and not every advisor should. And some students would really wilt under the sort of treatment I got, but that particular match was good for me, and I benefited enormously. Okay, I should tell you, before I actually tell you what I actually work on now, I forgot to even say I'm a professor at Ohio State, assistant professor. Before I tell you what I actually work on, I should probably tell you one more anecdote that's sort of formative for me in a scientific sense. So when I first, during my first year of grad school, I remember having this feeling like, okay, this is it. Like, I'm going to try to be a physicist. And that was a sort of strange and intoxicating thought. But I felt like now that I'm going to be a physicist, I should try to, learn what the deal is with physics. Like, what are the issues that people care about in physics? So I went to like a Barnes and Noble or whatever and picked up, in the science section, what's a good book about physics? And it happened to be this one that was called The Trouble with Physics. It turned out to be like a long argument about string theory and how string theory was bullshit or something. But what I remember from it actually is that inside the book, there was this section where he takes issue with the way we evaluate young scientists and the way we evaluate them for jobs and such. And he was saying that a thing that we tend to do is to give strong preference to people who have worked with someone famous. We say, oh, this person wrote a paper with such and such famous person, they must be good. And he said, instead, we should look for people who have done independent work. So he said, I get really excited when I see a graduate student with a single author paper. And I remember thinking, wow, like it would never have occurred to me to write a single author paper as a graduate student. Like I would have vaguely guessed that there's a rule against doing such things, but there's not. And so I was like, okay, that got into my head. Like I'm going to try to write a single author paper. On my own, I'm going to conceive of an idea and figure it out and publish it. It's going to be amazing. And for about a year after that, I just remember like struggling with the feeling of what could I possibly write a paper about? And anything that was too close to Boris's work, to like the professional line of work that I was learning, I just felt too hopelessly lost. Like there's nothing that I know well enough to imagine writing a solo paper. Until one day it occurred to me that there was something that I knew pretty well, and that was basketball. So I decided to write a theoretical paper about basketball. And it was just really me wasting time on ESPN.com or something. And I had just learned about Lagrange multipliers. Maybe you guys, some of you know this already, but for me, it's something I learned in second year of grad school, what a Lagrange multiplier was. And I thought that it was extremely cool. So I had this funny idea of how to use Lagrange multipliers in a description of a basketball offense to optimize the performance of a basketball team, whatever. It was a kind of funny idea. And I did it very slowly in stages, but eventually wrote this paper. It had ridiculous diagrams in it that looked like this. But this paper got some traction, in fact, and it turns out that in the universe, there is a conference that's co-sponsored by MIT and ESPN, and they invited me to speak, and I wore a suit for the first time in my life, and it was pretty exciting, actually. It was a lot of fun. And actually, to this day, this is still one of my better cited papers. It has 71 citations. It turns out this silly paper I wrote as a grad student. Anyway, but that kind of, I guess, positive reinforcement basically convinced me that I mean, what it really did is it sort of enforced in me this idea that the universe is full of like random problems that can be described in physics language. And so if I ever feel like I'm, spinning my wheels and being uncreative, then, just take something in the world that you're already thinking about. Like for me, I was always thinking about basketball all the time, and then turn it into a physics problem. And so that kind of process became sort of core to the way I like to do physics. Like just, it's a big part of why I enjoy the job, this feeling like anything can be turned into a problem that you can, get excited about and make progress with in a physics style way. Okay, so that's the introduction, I guess, to me anyway. If someone asks me, what do you work on? Well, what kind of research do you do? I always sort of hem and haw, and then I just talk about various projects that I've worked on recently. And some of that stuff has to do with electrical materials. So this is This is a project recently about improving the efficiency of materials that convert waste heat into electric power. This one is about the quantum Hall effect down here and these amazing composite excitations that appear in quantum Hall effect. And there's stuff all over. And then you see weird stuff. There's basketball. This is a theory paper I wrote recently about the dynamics of prestige, like prestige in job applications and that sort of thing. This one here, and right, this one about human crowds might actually be my most successful contribution to science so far, working out something about how humans navigate through crowds. Broadly speaking, but if someone, anyway, I always give these unsatisfactory answers to what do you work on? And I just say, well, I'm kind of thinking about this right now. And someone says, no, but like, what is your line of research? What does your group do? What does your lab do? And I have to hem and haw and say something like, well, I work at the boundary of quantum solid state and classical mechanics, classical statistical mechanics. But what that really means is I like quantum mechanics and I like random things. I like random processes, things that are really disordered. And so I tend to find problems that work in that vein. And actually, what I'm admitting to you, which is that I don't really have a field or a consistent line of work, is something that was a source of a lot of anxiety for me for a long time. So when I was a graduate student or a postdoc and I didn't have a permanent career in any sense, you would hear people talk about their work or about their career paths, and they would start with things like, ever since I was a young child, I have always really wanted to understand X, and X was something like, why do we sleep? Or how does the sun shine? Or like, how did planets form? Or something like that. And then they would proceed to tell you this story about how all their work was aimed at this one question. And that was the thing that kept them up at night. And their work was aimed at one big, amazing question. And I never had that. And I felt like you're supposed to have a burning passion for some specific problem. And I never had it. And I felt like I always had to fake my way into having it. And it took me a very long time to realize that I just like figuring things out. Like, I just like posing problems and solving them and figuring stuff out. And that was okay. It took me a long time to realize that that's okay to be such a person who doesn't work on some specific problem that they care about, but just enjoys figuring things out and lets their mind wander all over the place in an undisciplined way. That it's okay to be such a person. And I am such a person. So there we go. Okay, I should also, I'm sort of going to imply to you how wonderful it is to be a, academic physicist, to be a physics professor. But I always feel like when I do that to young people, I have to give them some counterbalancing sense of what a long and difficult road it can be sometimes to get that job. So my personal timeline was something like this. I was an undergrad for 5 years because, as I explained to you, it was such a hard process for me to figure out what I liked and what I wanted to do. I managed to finish my PhD in 4 due to my 3 hours a day of talking to Boris Shklovsky. But then I sort of spent 8 years in purgatory as a postdoc. These were at 3 different institutions. First, I stayed in Minnesota, and then I was at Argonne National Lab outside Chicago, and then I spent 4 years at MIT. And a postdoc is, on the one hand, it's like a wonderful time when you have just complete freedom and very little pressure on you, and you're learning really quickly, and you're making friends, and you're doing real research, and it's exciting. But it's also really stressful because you don't have a permanent job, and you know that most postdocs will not get to be faculty. Most postdocs at least in condensed matter theory, most of them are going to end up in some industry job after failing to get a job. And so the whole time you're just really stressed out about, am I going to get a job? Is the work I'm doing right now good enough that someone will want to hire me permanently? And so I spent a long time in that kind of limbo and just went through a lot of application cycles. So this is the full total of the wreckage. I applied to 10 grad schools, 21 postdoc positions, and 99 faculty positions, had 15 grueling interviews before someone finally offered me a permanent job. And the job I have is really good. I really like Ohio State. It's a wonderful institution with great people. But there were many times along the way where I thought I was done and that I was going to have to go find a job at a software company or something. And so that's the reality of the market right now. And I don't mean to discourage anyone. I just feel like I owe it to you guys to tell it plainly. All right, if you want all the gory details, I have a physics blog that is sporadically maintained at this point, but I did write a sort of post-mortem on what it's like to get an academic physics job. And you're welcome to read this if you want. Okay, so that's basically it for the bio part. I'm sorry that I rambled on for so very long, but now is the part where I switch to telling you about a cool science problem. Unless there are questions, I'm happy to dwell on this longer.
Do people have questions? If you have questions, feel free to raise your hand, or yeah, or just yell. It's fine. There are few enough people.
What made you keep doing the postdoc position instead of, going anywhere else?
Yeah, I have thought about this multiple times. Because you're so scared of like failing out of the academic track. And that anxiety is just unpleasant. And it's also true that the people who do leave the academic track and who end up working in, Wall Street or as a data scientist or something, they all swear to you up and down that it's wonderful and you should just get out, like that the alternative is so much better. So given that situation, you're always asking yourself, why am I still doing this? And there's like a more optimistic answer and a more pessimistic answer. The pessimistic answer is that you develop like a kind of Stockholm syndrome for your field, where you feel like I've invested so much that must mean the same thing as I just passionately love this field and I can't bear to give it up. When the truth is that like you just can't bring yourself to walk away. So it's very possible that that's what happened to me and what happens to lots of people. But it's also kind of true that, I don't know, for me at least, I really felt like I had fallen in love with this field and I had fallen in love with a job that lets me think about whatever I want. Like no one will tell you, today you must be thinking about widgets, or you must be thinking about like the metrics that quantify performance of whatever. I could really let my mind explore what it wanted to explore and gravitate toward the things that I thought was most exciting. And that freedom was just so intoxicating to me. I feel like I couldn't drag myself away from it until the bitter end. I guess that's the best answer I have.
Makes sense. Thank you.
There's a question in the chat, which is when are you going to write your next blog post? But I don't know how serious that question is, but
yeah, I don't know. Yeah, sorry. The truth is that in this blog was probably one of the best things that came out of my graduate school, and I wish that I updated it more. But so I don't know. Someone has sort of roped me into writing something, and when I write it, it'll probably end up on my blog. The other answer is that I waste too much time on Twitter when I used to spend it on writing a blog posts, and that's like my leisure time now, unfortunately. Okay, so sorry, someone else asked me, did you have to apply for the postdoc each time, or was there an automatic continuation? The answer is, okay, let me go back here. The answer is that it sort of depends. The typical postdoc position is either for 2 years or 3 years. So you'll see that, I didn't apply every year. That some of those years, it's like someone told me you have a guaranteed extra year, so just don't bother. So it sort of depends. Like a postdoc contract is something that usually lasts 2 or 3 years. But sometimes even when you have a guaranteed other year, you see a job opening come up and you feel like I can't afford to miss this one, so I'm going to apply even though I have another year guaranteed. So I don't know. That's maybe the best answer I have.
So I have a question.
Yeah.
This is a little bit different from the question that, well, you talked about your PhD advisors like mentoring style, but do you have any comments on, you said something about a very particular way of thinking about physics. Like, what did you mean when you said that?
Well, yeah, so there are different, I imagine like different axes that you can lie along. So there's what I would call formal versus intuitive is one axis, meaning that you like to write down governing equations and manipulate them until you get to the end. And some people are just extremely skilled at that kind of manipulation. And some people like to think about things in a very mathematical way. Boris was on the extreme opposite end of the spectrum. He was an extremely intuitive person, that he would just sort of intuit physics as almost like a narrative. Like anytime he talked about physics, there was always a good guy fighting a bad guy. There was always like a challenge that had to be overcome by the hero. And he turned everything into like a story. And that way of storifying physics, I guess, is what a lot of times people call intuitive, that you can almost just sort of guess the answer and then come up with a very clever argument based on your guess. And that's sort of the way he was. Another axis is something like numerical versus analytical, like how much you like to work based on computer simulations and numeric simulations of things. And Boris was the exact opposite, having grown up in the Soviet Union where there were no computers to be used exactly, unless you were willing to travel across the city with a box of punch cards. So he liked things to be as pencil and paper as possible. So that's another part of a style that I used. It's hard to convey a lot more of the nuance there, I guess, but I guess what Boris in particular had a genius for doing was taking a complex problem and then just simplifying it, like cutting out all the extraneous elements until you got to some very, very basic thing that you could reason within your head. That he could sort of cut away all the stuff that didn't matter in some way that always just felt like magic. There was no recipe for it. He could just do it. And that's sort of a thing that I learned from him. Physicists always talk about how, of course, you should do simple things, but the way in which they make things simple is different. And he had a real skill for identifying the core concepts at work. And I guess that's another thing that I noticed from him, I learned from him. He felt like, I guess here's another way of saying it. In his style of doing physics, you should never do a calculation until you know what the answer will be. Like you should have a non-mathematical way of reasoning your way to the answer. Or if it's mathematical, it's only like at the level of simple algebraic relations. And any problem can be solved at that level of thinking with concepts and with algebra. And you say, aha, I know more or less what the answer is going to be. You have some like irrefutable line of reasoning. And only then you do a calculation. Some people are the exact opposite. They write down the hard calculation and they do it. And then after it's done, they say, oh, I bet this means X. But he was the opposite. He had to know what was happening first and calculate after you know what the answer has to be. So, okay, that's maybe the best sketch I can give you. But
thanks so much.
All the great scientists have their own strengths in their way of thinking, and learning how to think from them can be a pretty exciting part of your training. Okay, I've prattled on quite a bit, I'm afraid, but maybe I can tell you about some actual science. So this is about what I might call the phase transition in the dynamics of quantum entanglement. And this is work I did with three very clever people. Adam Nahum, who's at Oxford, about to move to Paris, actually. Jonathan's at Bar-Ilan University in Tel Aviv, and Stithity Roy is a postdoc at Oxford. I want to make clear that I don't have to get to the end of this, so interrupt me or tell me when my time's up, and it's not a big deal. But I sort of mentioned that I like problems with quantum mechanics and I like problems with randomness, and this happened to have both of those elements. So this is a talk about quantum entanglement, and maybe let me just sort of set the stage a little bit by telling you what quantum entanglement is or how we think about it. And generally, we say that things are quantum entangled when the state of the system cannot be specified by describing all its components independently. So by state, I mean like a wave function. And if you can't write the wave function as a product of two independent pieces, then you say that those two pieces are entangled. So formally, we say that your wave function looks like a product state of a wave function for A and a wave function for B. Say, we always think about spins for some reason whenever we're talking about entanglement. So you have two spins. And if you can write the state of the whole system as the wave function for A times a wave function for B, you say they're unentangled. And in contrast, an entangled state is something for which that's not possible. So the canonical example is always this singlet state that looks like a sum of a term that's A is up and B is down, and a term that's B is up and A is down. So this is the singlet, and it's entangled in the sense that you can't write it as something of A times something of B. But the problem with this definition, well, okay, let me just suggest to you a different way of thinking about this, slightly different from that sort of canonical way, which is that two things are entangled when making a measurement on one part alters the state of the other part and reduces the set of possible measurement outcomes. So just to be a little pedantic here, in this initial example where A and B were sort of independent of each other, if I make a measurement of the state of B, it collapses the wave function into something that looks like, okay, B is in the up state, and now A continues to be what it was. So if after making measurements of B, I make measurements on A, I can have any outcome that would have been the same range of outcomes as if I had never made the measurement on B. Now, on the other hand, if I'm in this singlet state, once I measure B, I collapse the wave function into the sector that's consistent with B being up, say. So now I've collapsed the wave function to something that looks like A is down and B is up. And now any future measurement of A will definitely yield only down. So by making the measurement of B, I have reduced the set of outcomes on A from either up or down to just down. And that's how I know that they're entangled. Anytime making measurements on B reduces the set of possible measurement outcomes on A. So the nice thing about that perspective is that it immediately suggests a way of quantifying how entangled they are. Are they just a little entangled or a lot entangled? And the way to ask that question or to quantify the amount of entanglement is to ask, if I completely measured the state of B, then by how much would I reduce the set of outcomes on A? So the way you can think of it is like an entropy of a total possible set of outcomes for A, and ask by how much is that entropy reduced by measuring everything in B. Okay, there's some details I won't go into, but that object is called an entanglement entropy. And it basically tells you how much measuring B will change the set of outcomes on A, or equivalently, how much information about A is stored non-locally in B. Okay, so this kind of question, like asking about how entanglement evolves in time as a dynamical quantity, has really been something that we're only really starting to think seriously about as a community. And so if you ask the question, I have some quantum system with many particles, and I want to know how the entanglement evolves as a function of time, that could be a hard question. And one of the big tools that we use for addressing it now is called the quantum unitary circuit. Okay, so here's a picture, and the way you should read this picture is down here at the time 0 point in the axis, you have some quantum state. Like suppose you have a bunch of spins and all the spins are up. So you're in a definite state where they're all pointed up. And now as a function of time, you describe the dynamics as a sequence of discrete events. This is sort of a simplification or a way of turning continuous time into discrete time. You imagine that your system is evolving by a series of discrete operations, and that's what these green bricks are supposed to indicate. So a green brick, that connects two lines basically means you grab the two spins and then you do some operation on them that leaves them entangled afterward. So we call that a unitary operator. And you can have a circuit that sort of looks like this one on the left, where gates or these unitary operators are sporadically arising at different time and space locations. Or you can have something that's sort of regular and orderly. This is sort of an approximation of, say, a continuous time Hamiltonian, where nearest neighbors are interacting with each other continuously. It becomes a way of approximating continuous time dynamics. Anyway, in this talk, I want to talk about random dynamics. And by random, I mean that either these green bricks will be random, like there will be some random operation that takes the two spins to a random new state that's usually entangled in some way, or something where the location of the operators is itself random. Okay, so this is a big field, entanglement growth, but the only thing you really need to know for the purpose of this talk is that entanglement tends to grow linearly in time, by which I mean, if I start with some state where there's no entanglement between left and right, say at time 0, all the states all the spins A and B are in some definite, they're all in some definite state. And now I allow them to start interacting with each other. The entanglement between left and right will start growing linearly with some rate that gets called the entanglement velocity. So the way you can think about it schematically is that, like, I have, at early times, I tend to grab two spins that are sort of close to each other and I entangle them. So that might, at some rate, I will entangle spins that are to the left of this partition with the ones on the right. And so I'll sort of have like a length scale over which spins are entangled with each other. And that length scale will continue to grow. So now I've entangled not just neighbors, but next neighbors, and then next neighbors, and so forth. And that range of entanglement will grow with time. As the range grows, so the value of the entanglement between left and right grows. That's a very simplified picture. And if I wait an infinite amount of time, then everyone is sort of entangled with everyone else. regardless of how far away they are in space. And at that sort of infinite time limit, you end up with a situation where you have an entanglement that's extensive in the system size. Basically that each spin has, stored half of the information about its value in the other half of the system. And that information is completely scrambled over the whole system. And you get what's called volume law entanglement, meaning the entanglement is proportional to the total number of spins you have in the system. Okay, so that was sort of the state. Okay, and that's not the whole state of knowledge, but we got interested in this question of what happens when you have that kind of random quantum evolution, and at the same time you're making measurements. So what I mean here is, suppose that I have some circuit and there are these green bricks that are making spins entangled with each other. And when spins get entangled with each other, they tend to mediate larger entanglement between two halves of the system. But suppose that's happening at the same time with someone coming along and making measurements. So that's this guy on the right. What he's doing is he's taking a spin and measuring its z component, up or down. And every time you do that, you collapse the wave function and you reduce the volume of the Hilbert space that it lives in. In other words, this spin can no longer contribute to anyone's entanglement because it has a definite value. So the question we wanted to know is, if you have these unitary operators that are, increasing entanglement, and you have these measurements that are reducing entanglement, what happens when both are happening at the same time? And basically, the whole result that I want to tell you today is that there is a phase transition as a function of the measurement rate, by which I mean there is one parameter in this kind of problem, which is how frequently you're making measurements. And if that measurement rate is smaller than some critical value, then your entanglement will continue to grow linearly in time until it saturates something of order the system size. The entanglement velocity might be a little smaller, but you'll continue to grow. On the other hand, once the measurement rate becomes larger than some critical value, then suddenly the entanglement stops growing. I mean, abruptly, you have an abrupt change where that separates a state where the entanglement grows from a state where the entanglement doesn't grow. And this transition can be described as a phase transition in the same language of water freezing into ice or something like that. It separates two qualitatively different states by an abrupt change. Okay, so there are two. Now I'm giving you my outline slide 45 minutes into the talk, but that's okay. There are two different ways to think about this. One is in this sort of 1+1D setting. And then if I have any time, I'll tell you something about how it looks when you have everyone coupled to everyone else. Okay, so first, what we actually did is the system we're actually describing in this first part is, say, a one-dimensional line of spins or qubits or whatever we want to call them. And there's some regular pattern of unitary operations that are entangling them. And then at each point in time and space, these are these black dots, you have some finite probability of making a measurement. So I don't mean that all of these are measurements. All of them are some probability of making measurements, and the measurements are randomly distributed in time and space. And then you can ask, what happens to the entanglement entropy as a function of time? And my claim is that when the measurement rate is smaller than the critical value, oh, sorry, this is a typo. I gotta fix this right now, or it's gonna kill me. Okay, let's try that. My claim is that when the measurement rate is smaller than the critical value, the entanglement continues to grow. And when the measurement rate is faster than the critical value, it quickly saturates to a constant that's independent of the system size. And exactly at the critical one, it grows logarithmically with time. Okay, so how do you understand that? Let me give you a sort of visual picture of how to think about this problem. Suppose I told you that I have an initial state of spins, say they're all up, and then as a function of time, they go through a protocol that's described by this circuit, where each of these green things is some entangling operation. And then I were to ask you at the final time, given this circuit, how entangled is this left half with this right half? Okay, anyone want to guess how much entanglement is there between the left half and the right half given this picture? Go ahead, yell it out.
No entanglement between
no
the
entanglement,
sides?
right? It's clearly zero, because there is no way that, what's clearly happening is that everything to the left of this line is getting all entangled with itself. Everything to the right is getting all entangled with itself, but never is there anything that couples something on the left to something on the right. So there's no entanglement. Just like was Sabrina, was that right? Just like Sabrina said. So one way you can think about that is I can draw this red line that separates left from right as two disconnected pieces. Okay, so let's try something a little more advanced. Let's say I have something that looks kind of like that same thing, except now there are these operations that connect left with right. But in addition, I'm making measurements. That's what these circles here are. And particularly, I'm going to take this spin right here, say it's spin 4. It's right next to the midplane. And I'm just going to keep measuring spin 4 over and over and over again. So what's going to happen is that after time 1, say 1 gets entangled with 2, 3 with 4, 5 with 6, 7 with 8. But then immediately after it, I'm going to measure the value of spin 4. So now spin 4 is a different value. It's not entangled with anyone. Now the next time step comes along, and I apply this operation that entangled 4 with 5. Now the important thing is that 4 got entangled with 5, but 5 didn't get entangled with anyone else because 4 had a definite value that was independent of everyone else. So after the second time step, you say 5 is entangled with 4, but otherwise nothing on the right is entangled with anything else on the left other than 4. Then I immediately measure 4 again, so I can say, okay, 4 is disentangled from everything. And all I can say is that stuff on the right may be entangled, these 3 might be entangled with each other, but that's it. So now what I'm getting you toward is to imagine that every time I measure this spin, I prevent any entanglement from forming between left and right. By continually measuring the value of this spin that's adjacent to the midpoint, I sort of block entanglement from forming between left and right. Now, in terms of this red line that I'm calling the minimal cut, you can sort of draw this red line, and it's like the red line can pass through the locations of measurements for free. It's like the measurement is a place where that spin is causally disconnected from its past. And so I can convince myself that nothing to the right of this line can depend on anything to the left of this line. So again, at the final time, they are disentangled from each other. Okay, you can play with a bunch more examples if you want, like say this one, where early times I've let lots of stuff get entangled with lots of other stuff. And then at some time I measure everything to the left. And then I do again this game of just measuring the one next to the midplane. And you say, oh, there's a cut that goes like this. It passes through the locations of the measurements. And now everything that's inside this cut, this top left corner, is causally disconnected from everything outside it. And consequently, the state of all the spins on the left at the final time can have no relationship with the state of the spins on the right. So that's this concept of a minimal cut. Now, what's interesting is to ask the question, well, let's just suppose that I eliminate one of these measurements. Look, let's take this one right here and just say that measurement never got made. So now I can no longer make any strong arguments about how, the left half is definitely disconnected from the right. But what I can say is that the only thing that connecting them is the value of one spin at one particular time. And I know that one spin cannot convey more than one bit of information. Like that one spin is just in some superposition of up and down. So the most information it can possibly convey is one bit. So what I can say is that what I know is that there may be some entanglement between left and right, but it is at most one bit. So just by virtue of this one that was uncut. And this was actually a very clever realization put together by some of my collaborators. And the general form is like this. So you draw yourself this circuit in time and space. You say anywhere there's a measurement, that's like a broken leg of this circuit. And then you ask the question, okay, given that at the final time, I want to separate, say, left half from the right half, how many additional legs of the circuit would I have to break before I could just pull them apart? If there are many measurements, then maybe they come apart already, or maybe I just have to cut one or two others. But the point is that the minimal number that I have to cut will put a bound on how entangled they can be. And we'll call that entanglement the minimal cut. And what you may notice is that this has become, from a very quantum sounding problem, this has become something that sounds like a very classical problem. And in fact, the kind of problem that this is called what you call first passage percolation problem. Okay, so when Adam and I first figured out that this mapping, I got tremendously excited because the very first college physics class that I took was taught by this guy named Dick Zalin. He was a famous cantankerous old guy who worked on semiconductors for a long time. And he taught us about this problem just sort of on a random digression in a class. He taught us about this problem that he called the vandalized resistor grid. And he said, imagine if you had a large square grid of resistors, and each link in this grid had a 1 ohm resistor on it. And now you're going to say apply 1 volt across the opposite edge of the grid and ask what's the current. Well, you can figure it out pretty quickly. It's 1 amp. 1 amp of current. The effective resistor thing has a 1 ohm resistance. But now the interesting thing is what happens if someone, this vandal here, starts going in and randomly cutting links, just choosing a link at random and then cutting it. Well, as you cut them, you reduce the number of current paths. You concentrate the current. The effective resistance goes up. The current starts to go down. And then if you cut a certain fraction of them, the grid will randomly fall apart into 2 disconnected parts. 0 current can flow. So there's a critical fraction, turns out to be 1/2, where current just suddenly stops flowing, and the left half of the circuit and the right half become completely disconnected from each other. So in a sense, the problem that we're solving is very analogous to this problem. And now let me make the analogy a little more clear. So here's the circuit in time and space. So I sort of said that the problem we're eventually solving is the question of how many legs of the circuit do I have to cut, given that some fraction of them are already cut by measurements. So okay, if there are no measurements, that's p equals 0, then you just have like a big chain link fence with no links that are cut. And if you want to separate the left half from the right half, you have to make some cut that goes all the way down the system. And the number of cuts you have to make is just proportional to the length of the system in the vertical direction, which is the time. So I would say, oh, then the entanglement is proportional to the time. Now, if I have a bunch of measurements, that's like a bunch of these links have already been pre-cut for me. And how do I think about this? Well, it turns out this was something that Shklovsky worked on and taught me how to think about. And he said, when you have a network that a bunch of links are cut, you should think of it kind of like a ripped up net. Like it's a net that has a bunch of little, parts of it that are hanging off. So it's maybe tattery in some parts. But there's like a backbone, this thing that we call the percolating backbone or the infinite cluster. And that backbone is what holds it together. And the more you cut, the bigger the holes in the net become. And in fact, the way they change is some equation like this, where it diverges at the critical value. And those holes just keep getting bigger and bigger. And along the way, there may be little dangling pieces or little parts that fall off your large net. But if you want to ask the question of how many additional cuts do I have to make to pull the net apart into 2 pieces? Well, roughly you have to make 1 cut for every, this distance psi is called the correlation length. It's like the typical size of big holes in the net. You have to make 1 cut per correlation length. So maybe 1 here and 1 here and here and here and here. So the number of cuts you have to make is like t, the size of the system in the vertical direction, divided by psi, looks like t over psi. So what you get, now mapping the entanglement to the minimal cut, you get something that looks like t over psi, or in other words, an entanglement that still grows linearly in t with some velocity that gets renormalized, reduced farther and farther as the number of measurements gets closer and closer to the critical value. Okay, finally, on the other side, you have something that looks like this, where your net has now fallen apart into pieces, and at best you have just little clusters that by chance are still holding together. So if you start your cut, say, in the middle of the system at finite time, all you have to do is cut your way out of some little cluster, and then you're free. All of this stuff is given to you for free. And the question of how much entanglement is there between the left half and the right half at the final time is basically just how many cuts does it take to get your way out of this little cluster. And that ends up being logarithmic in the size of psi. Basically, this psi is like a fractal object with all length scales represented equally up to the size psi. Right, so what you get in the end is something that looks like this. When you're below the critical measurement rate, you have something that grows linearly in t with a renormalized velocity. Then you get logarithmic right at the transition, and then you get something that's constant, has no time dependence above the transition. So you can do numerics on this. We did some numeric simulations, and this is what it looks like in sort of log scale. And what you're seeing here is the entanglement growing linearly. And now, because this is a log scale, a vertical offset means that the slope on a linear scale is changing. So you see the slope declining, getting closer and closer to 0 as you approach that special critical value where the circuit falls apart into pieces. And then above the critical rate, you find the entanglement doesn't grow with time anymore. It just saturates to some constant value that has no relationship with the system size. So if we plot it like this, and I look at this entanglement growth rate as a function of the number of measurements, we see this, see here the blue dots, you see this beautiful curve, and this red curve actually is not, has no fitting parameters in it at all. It's exactly the classical percolation result. And so this is the figure from Dick Zallad's textbook, and this is our data, and it really turns out to be one problem mapped onto the other. Okay, so last thing I think I'm going to tell you here is just if you take different curves, so this was sort of, sorry, let me go back. These curves were sort of imagining the system size going to infinity and asking how the entanglement grows as a function of time. You could instead take a finite size system and ask what's the entanglement at infinite time. And if the system is going to its fully entangled state, then the entanglement should grow linearly with the system size. So what you're seeing here are different values for the entanglement after a very long time for a different system size. And what you're seeing is that when the measurement rate is small, the entanglement continues to grow with the system size. It's approaching that volume loss state where the entanglement is just everyone entangled with everyone else. On the other hand, if the measurement rate is larger than some critical value, then suddenly the entanglement doesn't depend at all on system size anymore. Everyone has a similar small entanglement. And so you can sort of identify this point where the curves come together. That's exactly, in this case, the classical percolation threshold. Now, maybe the last thing I'll say here, now that we're sort of out of time, is that the problem that we solved is not exactly the real problem. It's sort of a mapping or an analog of the real problem. And if you really want to solve how does the real entanglement entropy behave, well, you have to do some numerics. It's hard to get an exact solution. We do some computer simulations, and we see very similar behavior, except that this threshold has moved to a different value. And there's some clever way to scale these curves on top of each other to exactly measure this value, and it's hard to say. But it moved to some different value, and we can't predict where it should be. We can only measure it numerically. And so the situation is kind of like this. As a function of the measurement rate, you have a state at very small measurement rate where the entanglement is very large. It's extensive in the system size. You have a state at very large measurement rate where the system has fallen apart into disconnected pieces, and therefore it literally cannot be entangled. And then you have this sort of no man's land in the middle where the circuit is not literally disconnected. It is tenuously connected. But nonetheless, the system does not generate an extensive amount of entanglement. It's like those connections that remain in the circuit are somehow too tenuous to allow extensive amounts of entanglement to persist. So when we first proposed this, there was a lot of pushback and people with competing results. And I think finally there's some consensus. It's been a fast moving field, but unfortunately there's no real solution for what's happening here. We can solve this classical connectivity problem really well, and this part we can only do numerically. So the second part I was going to tell you is that how there's a modified version of this problem that is possible to solve, and how we managed to solve it largely through the cleverness of my collaborators. And it's basically the problem where everyone is connected to everyone else, where basically instead of having a regular 1+1 dimensional circuit, you have something where you grab two qubits at random, entangle them, and then grab two other ones and entangle them, grab two other ones and entangle them, and so forth, in a sort of random process that has no spatial structure. This model gets called the bag of bits model. You imagine it's throwing all your qubits in a bag and then grabbing two out and entangling them and throwing them back in the bag and shuffling it again, like you're playing Scrabble or something. I'm not going to tell you how we solved that problem, but we did, and we got super excited. But I want to tell you something pretty cool, which is that there's a reason that people care about this problem, which is because there's this proposal by Matthew Fisher at Santa Barbara that this exact problem is very important for how the brain operates. So he's been trying for a long time to investigate the idea that quantum coherence is somehow very important for how your brain works. And that's an idea that has a lot of pushback because people are saying, look, it's a messy, wet environment at room temperature. You know how hard it is to protect something from from decoherence in a wet environment at room temperature. But he has basically identified a certain set of molecules that have very well protected nuclear spin. And he's saying, no, those particular molecules can have a nuclear spin coherence time of minutes. So you can have a spin that remains in a definite quantum state, even in your brain for minutes at a time. And then you go, okay, well, how does that do anything? And the mechanism that he's proposing is basically that these spins, are in some, watery environment in your brain. And if they happen to bind together in just the right way, then those two spins interact with each other and they become entangled. And then the two molecules can separate again. And then the important thing is that molecule now that is in an entangled state with some other molecule for minutes at a time can bind to a synapse in the brain. And depending on the spin state of the molecule, it will either get endocytosed into the synapse, pulled in, or not. That the state of the spin in that moment of interacting with the synapse is important for what happens to it. I don't remember the details. But he's saying that now whether something gets endocytosed into the synapse or not determines whether the nerve fires. So he's like, now I have a mechanism by which you have a soup of spins and their quantum state determines what happens with the nerve firing in your brain, and they can be entangled. Anyway, okay, it's a bit of a long shot, but it's a real proposal. And what it sounds like exactly is a soup of spins that can get entangled with each other and get measured. And now you want to know the question of, can entanglement persist for a long time or not? And that's the question that we were able to solve. And I'm sorry, I don't have time to go through it. There was similarly a classical problem that we were able to solve that comes down to a problem of a random graph. And then we turned it into a problem of quantum evolution on a tree structure. And we derived this crazy result for the true quantum transition that is this value right here with the 75 pi's in it. And we can derive the classical transition that's separately. And we were able to derive as well the behavior near the quantum transition. And we had this similar set of three behaviors. Okay, I'm sort of pushing my luck here. So here are my conclusions. Basically, what we're talking about is this surprising and quite fun problem about how quantum entanglement evolves and persists in time. And the really surprising thing to come out of it is that there's a phase transition. It's not like it's a dynamical phase transition. It's a phase transition in how something evolves in time as a function of this measurement rate. And who knows where this is going to go next. But okay, at that point, I think I'll stop, and I'm happy to take questions from you guys now, or criticisms, or whatever you like. Okay, I see one question in the chat from Sabrina. Why does entanglement grow linearly in time? Does it mean that systems are constantly interacting and the outcome is governed by some physical law? So knowing information about one would tell you about the other. Can you give an example of the specific unitary operator? Yeah, let me see if I can give you the best intuition I can give you. So okay, one thing I can say for sure is that I am assuming, okay, let me go back quite a bit here. I am assuming that there's some finite rate at which you're applying these unitary operators that's continuing with time. So, okay, let's just go back here. So you could either have a regular structure like, sorry, yeah, this is fine. You either have a regular structure like this, where I'm just continuing to apply at some finite rate per time, unitary operators that connect the left half and the right half. How to properly understand this is actually a very non-trivial question. And I think the language that we've sort of settled on is two things have to happen. One, you have to have one of these operators that's connecting left half and the right half. But you also have to have a process where information that's on the left half doesn't just sit there, it spreads out. Like the local information that was the value of some spin becomes scrambled among all the spins on the left half. So on the one hand, you have these operators that connecting left half and the right half, but then at the same time, you have many other operators like these ones that are spreading out the information brought to you from the right over all the spins on the left. And as long as that information is happening, as long as those two processes are happening at the same rate, then you get this linear growth of entanglement. You can sort of, if you want, you can sort of think of this as a diffusion problem in Hilbert space. You start with a wave function, like you have a Hilbert space that's like 2 to the n dimensional. And you start with your wave function occupying definitely one corner of it. And then the more operators happen, the more you're sort of branching out into this exponential Hilbert space. And the entanglement entropy is like the logarithm of how many states in the Hilbert space you're occupying. So it becomes a quite non-trivial problem of evolution in this, of diffusion in this sort of abstract space. I don't know how to give you a much stronger conceptual answer, unfortunately. One thing I will say is that you asked about what kind of operators it have to be, and the truth is it doesn't matter that much. Like I was sort of imagining random operators, but you can use the same one every time, as long as that operator doesn't accidentally conserve something. Like it accidentally conserves the Z component of the spin or the total total spin or something like that. Then you have a slightly different problem where the conservation laws block things from really scrambling out. I don't know if this makes you any happier.
This makes some sense conceptually. I guess I'm trying to get like a classical intuition of this, if that's even possible. But I'm thinking like you have a bunch of like balls, and then if like two of them collide, you're gonna have some conservation of momentum and energy. And so if you measure one, you're gonna know something about the other, and you just like keep colliding them, then you're gonna have, I don't know, some chaotic system. But if you measured maybe like at some point certain things, you could separate those things into like, I don't know, so you have a whole bunch of air molecules. I don't know if this question makes sense. It's kind of confusing.
Yeah, I'm not sure that there's a really good classical analog like that, because like important for this problem secretly is that the Hilbert space grows exponentially with n. Like the number of possible states grows like every time you add one more spin, it doubles. Whereas, yeah, that's a good question, whether there's a really clear classical analog like that. And at the moment, I don't know the right one for you. I'll have to think about that. Maybe there's some good visual picture like that.
Thank you.
I had a question. Dr. Skinner, thank you. This was such a thoughtfully, carefully crafted and put together presentation. I'm sorry we didn't get to go through the entire PowerPoint. I don't know if you would feel comfortable or would think it appropriate if it would be possible to share this presentation with the attendees.
Yeah, sure. I'm happy to send it to you guys to distribute afterward. That's fine with me.
Okay, thank you.
I have a bit of a different question.
Sure.
So this is super cool. I have two questions. One, which is, okay, so one is you look at like this S0 like entropy, which is kind of, you know, I mean, it's neat, but like, I don't know. But they're like, you look at von Neumann entropy and then also like, but the higher moments conceivably could give you different transitions, right? Is this the case or like?
Okay, all right. So we've got an expert in the audience, and I should, I've hidden something here, I suppose. Let me see if I can unhide it. Oh, I did. Sorry, I don't even have it in this one. Okay, so let me put it this way. There is what we call the zeroth entropy, which is this minimal cut, and that provides a definite upper bound for all the others. There are certain special cases in which that upper bound is saturated that I didn't go into. Basically, it gets saturated in the limit where the spins are not spin 1, but spin s, where s is very large. In that case, you find that the upper bound gets saturated. But the question about whether the different Renyi entropies can have different transitions, it turns out that there's a theorem that says for n greater than 1, all the Renyi entropies are just within a multiplicative constant of each other. Like that they are both bounded from above and below by s infinity. And so you can convince yourself that for n greater than 1, even infinitesimally greater than 1, they all must have the same transition, the same critical point, the same critical exponents, and etc. Now, the question of how do you go from S0, which clearly has a different transition, to the generic transition where n is greater than or equal to 1 is tricky, and it's probably still not that well understood. But so basically, I guess the short answer to your question is that for n greater than 1, S of n, they all have the same transition. And for n less than 1, it's kind of no man's land, except that we understand S0.
Okay. The other question I have is maybe helpful to a lot of people, which is, this is super cool stuff. How do you like, and but like your result is also like super, okay, and it tackles a very complicated problem, but like the results you get have this really nice like picture resolution to it, right? Like in terms of minimal cuts and whatnot.
Yeah.
How do you go about doing this? So like what do you, like you may have started out with like some sort of problem, but like, okay, how do you go about doing this? Maybe I won't.
You mean how was that idea arrived at, the minimal cut idea?
Not even, I mean, like, how do you get your, like, do you start with numerics, or like how do you
Oh,
approach
yeah,
that?
sure. So the nice thing is that once you make a mapping like that, you can just sort of look up what's already known. And you can say there's some very clever people who have studied that classical percolation problem to death, and they know all the exponents, so you look up as much as you can. And you can sort of make scaling arguments. So sort of these pictures that I'm drawing about the ripped up net, for example, those are secretly scaling arguments. And so if you look up this exponent nu, then you know it. Now, all this data that I'm showing you is, in fact, so data like this, for example, this is very much, this is just a classical numeric simulation where we really are just, simulating a random network with randomly broken pieces in it, and then looking for, the shortest path that separates it. And then there's some algorithm for that we looked up. But yeah, there's a decent amount of numerics that goes in here too.
So did you establish the mapping to the classical problem exactly like first and then do numeric? Is that like, or as zero?
Yes, right. So the mapping to the classical problem, that was sort of previous work done by mostly Adam, who figured out that mapping. Adam is like an amazing wealth of knowledge about all these obscure stat mech problems. And so he's amazingly adept at mapping one problem onto another. And so he was the one who established that mapping in a previous work. And then we were mostly able to use it here. And the big step was showing that a measurement basically acts like a broken link. And you can still use that same minimal cut description.
I see. Okay.
Sorry, I don't know how satisfying that answer was, but
No. That's good.
Yeah.
People have questions.
I had a question. So you see the same like logarithmic growth of entanglement in like MBL systems?
I am not an expert on MBL. I
guess starting in like if you look at like an L-bit product state, and
I think the answer is yes, but I don't quote me on that. I think the answer is that MBL does have a similar logarithmic growth of entanglement.
okay.
But sorry, I shouldn't go too far out on a limb.
Gotcha.
On that.
Yeah, I was just gonna ask if there's any connection that you might make between the two contexts.
Yeah, sorry. The truth is that I am not native to this field, and I was brought in by being friends with these guys. And so if you ask me hard questions about MBL and stuff, I'm gonna have to say I don't know. And this is one of those instances, I'm afraid.
Gotcha, no problem.
Do other people have questions?
Well, thank you guys. It was fun. I was very, very happy to be your guest.
No, thanks so much this is really wonderful. And we're so happy to have you. And this is very neat.
No, thank you. It was a lot of fun. And I'll remember to send these slides to you. And anyone who wants me to send me a question offline, please do so. I'm easy enough to Google and you'll find me.
Okay. Well, thanks so much.
Yeah.